All right, welcome everybody to the first talk of the fall 25 semester of our virtual set theory seminar at the Graduate Center. So today we have Rahman Mohammadpour from the Institute of Mathematics of the Polish Academy of Sciences. And he is going to speak about specializing triples.
Yeah, thank you. Thanks for the invitation. It's a great pleasure to talk in New York City virtually. But also it's a pleasure that I am the first speaker. And thank you for coming. Please stop me if you want to know some definition or you feel that I am wrong. That happens a lot. Yeah. So this is about, I have written some definitions, but I will write more proofs. So this talk is about weak embeddability between trees. And this notion is very useful because it's kind of graph theoretically is like a kind of homomorphism, but people use different terminology, but it is also useful in the study of Arrangement trees and also in topology, in model theory, in particular in generalized descriptive set theory, at least the old school. Let me introduce this notion. The weak embeddability says that a 3T embeds weakly into another tree if there is a function that respects the strict ordering. It's not like if and only if. So that is called sometimes a strong embedding or monotone embedding, something like that. And then we can say that two trees are weakly bi-embeddable or equivalent if each of them weakly embeds into the other one. And this induces an equivalence relation over the class of all trees. And but moreover, if you take the quotient by this equivalence relation, then you get a distributive lattice, maybe class sized. But if you have a class which is good enough, and this includes, for example, Arrangement trees. With this, after taking the quotient, is a distributive lattice. And here I introduce several classes. So if we have kappa less than or equal to lambda and kappa regular, T kappa lambda denotes the collection of trees of height kappa and size lambda with no cofinal branches. And we omit kappa if it is omega 1, so as it is a standard. And A kappa is the collection of kappa arrangement trees. What happens is that these trees, these collections are so nice, and to see that there is something that we want to see why it comes up in the definition, in the proofs, is that we can take the disjoint sum of two trees, and this is it's like addition, and the product over trees here is level product. I think it was introduced maybe by Todorchevich, if I'm not mistaken. And this is that if you have two trees, TO times S is all the pairs in T times S such that the height of T in T is the same as height of S in S, right? And the order is product. So one node is below the other one if it is below coordinate wisely. Maybe I write black. So if we look at these two, um, um, I want to add a page here. Sorry, just I don't know how to add a page. Okay, so the point is that, for example, these classes of arrangement trees or this T kappa lambda, which we call lambda white kappa arrangement trees. So white arrangement trees, white kappa arrangement trees are trees of height and size kappa with no cofinal branches. The point is that this, for example, if we look at one of these things with these classes, with these two operations, is the um, algebraic representation of this lattice, distributive lattice, modulo by weak by embeddability. Okay, so this will we will work with this. This is very important in this the main definition of this talk. And so one question is that whether these classes have top element, as you can say in if you look at this distributive lattice, or you can say also universal object is the top element. The question is that whether there is a universal object in one of these classes. And also we can talk about the universality number, that is the smallest size of a universal family for that particular class. And this is like the same as dominating number, okay? So there are some simple facts. One of them is this due to Kuroba, that if we have a nice cardinal arithmetic, in particular in GCH-like world, then the universality number is not 1. That means there is no universal tree for the class of lambda white Kappa-Arrangement trees. And Todorcevich, this is not trivial, Todorcevich proved that Martin's axiom for omega 1 implies that there is no universal arrangement tree.
Rahman, could I ask you a quick question? So this definition of this T lambda kappa, the lambda is the cardinality of the tree, right? But is there any version of this where you talk about the sizes of the levels, like slim trees or something like that, that the width, so to speak, every level has a limitation on its size or something like that?
Yeah, no, because usually in all these results, people look at the successor case, so it's not maybe very actually it makes sense. Maybe I don't know. Do we have classes like we have trees like height omega 2 and levels of size omega? Very
But
narrow.
I mean, for example, if you talk about Ahrenstein trees like omega 1 Ahrenstein trees, their cardinality is omega 1, but the levels
Yes.
have to be countable, right? So
Yes.
this restriction on the size of the levels is kind of missing when you talk about only the cardinality of the tree.
Yes, but usually, what happens is that we are interested in wide trees, not narrow trees in
Okay.
general, right? But maybe if kappa is not weakly compact but inaccessible, maybe uh, there could be some nice trees to study, but still the size is kappa. I don't know if the levels are small relative to the height, then we can say much more or
Okay.
not.
I see. Okay.
But you are right that also could be a definition. I mean, a modification of this definition. But the really the most interesting case for people has been uh, orange trees and T omega 1, that is omega 1 white orange trees. And
Okay.
so A omega. And so Kuropa result for this case is that CH implies that there is no universal white orange tree. Yes. And I have a very simple observation, but I don't know why it was not previously mentioned anywhere. But actually, so universality number of kappa orange trees cannot be less than kappa because you can take the union, right? But actually, it cannot be also kappa, which is easy. Like you have you fix an arrangement tree T0, and you are given a sequence of kappa many arrangement trees T alphas, and then you pick some nodes different at each level. So like these red ones, which are T alphas, and the height of T alpha is alpha, and then you plant that T alpha there. I mean, after some identification. So, for example, this is T alpha, this is T beta, etc. Then you embed all the trees, right? You put just and this tree. I mean, it needs a simple argument by Fodor's lemma that this tree is a large, this construction. Trivially, um, it embeds every tree on the list. So the universality number of kappa arrangement trees is either 1 or is in the interval open kappa 2 to the kappa. And it is an open question. Maybe, the question is that is it consistent that we have we have the universality a universal arrangement kappa arrangement tree. This question is interesting because of this false result of Meckler and Van Anen. Let me first mention this. In an old paper about generalized descriptive set theory, Meckler and Van Anen claimed that under MA omega 1 there is a universal wide arrangement tree. And then, I mean, soon after it was realized that the claim was, the proof was obviously was false. And this remained a question until recently, some years ago, Jamonia and Shella showed that under MA omega 1, in fact, there is no universal white arrangement. And this question that whether there is a universal arrangement tree, it's very non-trivial, and it is still open. I think I mean it's very hard. It seems very hard to construct an arrangement tree that you can embed everything into that. Recently, Benelia, Magidor, and Van Anen showed that this is not the right spelling. Showed that actually for let me state it for omega 2, but it can be double successor of any regular. below weakly compact. So what we have kappa less than lambda, and lambda is weakly compact. Then in a generic extension, lambda is kappa plus plus, and there is a white kappa plus plus arrangement 3 that strongly embeds, meaning that the function is one-to-one. Every here white means exactly kappa plus plus white. Every white kappa plus plus arrangement. And here I am interested even in no results. I am interested in the proof given by Jamonia and Shella. So how they prove this, the result that there is no white arrangement tree, then we talk about case omega 1. Okay, they show that under MA omega 1, the first thing is Todorchev's result, that there is no universal arrangement tree, and then they show that there is CCC forcing that can embed any white arrangement tree into an arrangement tree. The first step, which the result is due to Todorchevich, and it's not needed, but it's a they reproved it with new ideas, and these ideas and method is interesting here. So this is here is the definition of product that we are interested, and the main definition in the proof is this. Sorry, this thing that if we have two trees, which is which we can assume that they're Hausdorff and Arrangement. Hausdorff means that every 2 point, it's like normal, people call it normal. For every 2 point which are not comparable in the tree, there is a largest point below both of them, right? So if you have 2 points, then there is a largest point like this. And the definition says that if we have two Hausdorff arrangement trees and we have a function which is like a specializing function, the usual one, but with some extra properties that whenever different points have the same color, then the height of the points are different, and at each coordinate the corresponding nodes are incomparable, and this is the most important part, that I haven't defined delta. Delta is delta of t of 2 points is the height of this intersection or meet, whatever. Sorry for so the height of the height of the meet of the first coordinates is strictly above the height of the meet between the second coordinates. And there is a reason for this, because weak embedding does the opposite job. So this is to prevent S from being embedded into T. So this is called, well, I have defined this here. So this is the definition of Hausdorff, and this is the delta T function. So here is that, this is not here. Okay, this is that this triple is specializing triple if the trees are Arrangean, and we have a specializing function on the product with these extra properties. And I am interested in this because I wanted to know why we cannot prove like using this. But if you look at the proof of the fact that specializing poset is CCC, then you realize that there is no difference between white trees and orange trees. You can use the same proof to say that under MA kappa or kappa white orange trees are special. So my question was why we cannot just use this technique to say that there is no white universal white orange tree. The reason is that these properties of this specializing triple. So assume that we have a specializing triple. Then, of course, trivially, this product is a special. Also, both trees are a special. And the first tree does not weakly embed into the second one. And this is because if you have a function from S to T which is weakly embedding, which weakly embeds S into T, then we can pick a sequence as alpha less than. Here I use here we talk about Arrangean trees, but it could be any kappa Arrangean tree for anything. So what we work with kappa equals 2 omega 1. So if we have this, then if we look at F S alpha, this pair may not be in this product, but we can assume that F is level preserving by passing to F prime of some node is S is Fs restricted to height of S. So maybe weak embedding sends it up, then there is a node at level of height of S, which is, for example, alpha. Then if you restrict this to alpha, and if you do this for all the nodes, then it is still weak embedding. Because the next point has to go higher. And then when you restrict to that level, then it stays the previous nodes that you handled. So we can assume that this is level preserving. And then this is in this product. But by this by just counting argument, there exists alpha and beta different, so that the coloring is the same, right? C S alpha Fs alpha and is equal to C beta F beta. And if we look at this definition, it says that okay, heights are different. Okay, we choose like this, and they are incomparable, and we can look at this maximum node below S and S prime and T prime, and then we have this property that delta S alpha S beta is strictly above delta Fs alpha Fs beta. But uh, but this is impossible because because um, um, because of what? Because um, let me write it here. If it is clear, I can skip, but maybe so. Now, if S alpha meet S beta is definitely below strictly even, right? This is strict ordering below both of them because F is increasing on the chains, and this implies that if S alpha meet S beta is still equal or below F S alpha meet S beta in T. But this contradicts these two. It's a contradiction. So this was I mean, put in the definition to prevent S from being embedded into T. Okay, now if we look at the definition, the original definition, even if you don't assume that these are Arrangean, you assume that they are white Arrangean. This is impossible because uh, they have to be Arrangean because of this property. Where is that? So if you have uncountably many nodes at some level, then you have to take the same value, and then the height must be different. Here, the first option. So it cannot be. You cannot put white trees. But then removing some of these properties to handle the situation causes some problems. So this modification I made is just the necessary things. So I call it left specializing triple, but it's not a good name, doesn't matter. So we have a triple as before, but now you can assume SNT or 3, so everything, whatever. But let us assume that SNT are right. And there is no name for this, but are white something, some lambda white for different different sizes, maybe kappa arrangement trees, and C is as before, but C is defined maybe on a restriction of this product to a set. U is a subset of kappa into sorry, it's a kappa plus 3 is into kappa.
So you mean restrict U is the set of levels, so to speak, that you restrict?
Yes,
Okay.
yes,
Mhm.
yes,
Okay.
just
Mhm.
those levels. So we can assume that it is unbounded. This is the interesting case. And then this is as before, except that if the color is the same and but the points are different, if the height is the same, then the first coordinate are equal. This just implies that the first three is Arrangean. However, we don't need it really in some sense because we will make the first three will be made by a forcing, and so we can handle it to be Arrangean. And if they have the different heights, then uh, uh, then uh, this is not comparable with S is not comparable with S prime, T is not comparable with T prime, and delta of S and S prime maybe delta of S and S prime is bigger than delta of T and T. This delta is in T, this is in S. Sorry, I confused the notation. Okay. So what else? We don't require that the heights are different necessarily, but we have this property, which is important, of course. Now, the point is that if you have such triple, then S and T are both of them are special on U. That means S restricted to U and T restricted to U are special, and uh, uh, S is Arrangean, kappa Arrangean, yeah, kappa plus. And S does not quickly embed into T. So this is not very different, but since the proof you used some of the properties of usual specialization, in particular these heights are different, etc. But also it makes some complication in the proof, and I want to talk about that. So good that I have time. Now let's look at any question so far. Okay. So let us see how they prove this. Okay. The forcing they use is that you have a arrangement tree, the original forcing. T is an arrangement tree, and you want to construct this function C and also add an arrangement tree S, which does not embed into T. That these three objects together make a specializing triple. So let me use the yeah. Okay. So the conditions are the forcing. Let's call it I don't know, PT. Has so a condition P consists of is a quadruple UP VP and an ordering and also a function. Okay, we are approximating the arrangement tree and also the specializing function, but we need to be careful. So one is that UP is a subset of omega 1 and an artificial object just for the root. This is finite, and VP is a finite subset of T. And UP with this ordering is a Hausdorff tree with root star This is just for technical reason. It's not important. And so that means it's Hausdorff. That means for any x and y, we have an object like this. We denote by x meet y, which is the largest point below both of them. Okay, and we require something more. That is, here we want that the final tree be on omega 1, be it and levels are these intervals. That is this is gonna be, I don't know, level. Let me. Okay, some of them, I mean, most of them have this as a level, but for some, yes. Okay, most of this level will be in exactly these intervals, and we denote this alpha. So if we have beta in this, then h beta is alpha. Is the finally will be height, but here is well defined. Okay. The fourth condition says that for any t in VP you pick, there exists x in UP such that height of t in T is the same as this hx. We need it, right? Because of this definition of the product. And CP is a finite approximation of the specializing coset, but this is defined on UP times VP. And into omega with the same requirement as C in a specializing tree. Here, this is the original definition of Myrna and Shell. And if there is one thing here that is very important, that technically is very important, is that this is defined only on limit levels. That means I put limit here. So if a point has height, is of success or height is not in the domain of CP, this function. And the ordering is natural. P extends Q if and only if UP extends UQ as a set, VP extends VQ as a set, CP extends the ordering is also maybe UP with the ordering extends as 3 this one UQ, and VP extends as a set VQ, and CP extends CQ as a function. And the most important one is that for any x and y in UQ, the meet is in P is the same as in Q. So we don't change the meet. We want to work it finally for the generic tree. So if we move it, then maybe it doesn't exist. It goes away. So these are natural, right? And it's the same. So any question about this? Okay. So So the approximation is adding um, an omega 1 tree, but also this finite function CP makes sure that it doesn't get any cofinal branches, so it will be orange on. And it tries to make this function on the product of the generic tree and the given tree, but on the limit levels. It doesn't change anything, but it's very important in adding a page. Yeah. It's very important in the proof. So now the point is that what happens if you want to prove that this has countable chain condition. So we can guess how the proof goes if you are in particular familiar with the usual specializing forcing of a tree, is that we can find using this lemma, Baumgartner, Malitz, Reinhardt, which says that if you have an uncountable collection of finite subsets of a tree, and the tree is of height omega 1 but has no cofinal branches, then there is an infinite set, or at least there are two, that for any two sets, in this infinite set of finite subsets of T, so that anything which is not in the common part from one side and one from the other side are not comparable to each other. This is how you prove the chain condition of the specializing forcing, and this is how Baumgartner and Malitz and Reinhardt showed that it is consistent, that every arrangement tree is special. Now, if we come here, okay, we have this part for VP which comes from T, and we can have the same argument more or less, but then okay, we have this extra function, we can handle it with delta system lemma, etc. But the point is that now we need, when we want to merge two conditions to find the common extension, we need to define the intersection between the points. And this is gonna be complicated because it cannot be arbitrary. One technical thing here that was why they use limit levels is that, okay, we can say if we are able to define the intersection between points, we can choose them to be successor. So then successor ordinals, right? Because these are ordinals in omega 1. Then, okay, then we don't need to define the function on those nodes. At least this is a relief. So it remains that how we can handle these intersections, in particular because we want to have this property. These ones. So this could be what to say? Why this is? Maybe you say that, okay, we know that. Okay, so sorry. Now here, if we have, for example, two conditions that we have this Baumgartner, Malitz, Reinhardt for that, they are in that sense incompatible. Then maybe for example we choose an intersection for one point from UP and one point from UQ, so one here and one from the other one, but then there are different T's from VP and VQ that can come, and they have different intersections with each other, then they must be also handled. So this is a nice proof. I like it due to Mirna and Sahar. Um, so let us see how far we can go with just with the usual things about specializing forcings. One thing is that if we have a collection, sorry, someone has a question. If we have omega 1 many conditions and we want to say that there are two which are compatible, then what we can say, these conditions are like, since the tree is narrow, is Arasha, the given tree T, it is like, okay, let me make some picture. It is like that I have P0 and then I have some level alpha 0, or maybe gamma 0, and then uh, it has some objects here from U, some objects from V, above the height of whose height is above gamma in T, and then I have also more points, and then I have other conditions, P alpha, gamma alpha, and they have something, maybe they have something here below, from both sides, from U and V. I mean, just this is notationally, I mean, from omega 1 or from T. Then we can use this standard, some kind of argument to do disjointification that and make them kind of coherent or compatible in the core. So using Fodor's lemma, delta system lemma, etc., we can all kind of shrink this collection to a nice collection, P alpha alpha less alpha in let's say X subset omega 1 unbounded, that what is, they have the intersection, for example, for any alpha less than beta in X, we have this gamma alpha, so P alpha intersection gamma alpha, sorry, kind of restriction, but we should be careful about writing this. P alpha intersection gamma, sorry, U alpha, if we let P alpha is U alpha, V alpha less than alpha, and C alpha, the same for beta, right? We can arrange this as U alpha intersection gamma alpha is the same as U beta intersection gamma beta, and this is the same as U alpha intersection U beta. This is delta system argument and Fodor's lemma. And the same V alpha intersection T less than gamma alpha is the same as V beta intersection T less than gamma beta, and this is equal to V alpha intersection V beta. And we can also, this is disjointification, saying that U alpha is a subset of beta, V alpha is a subset of T less than beta, and what else? Yes, so if then maybe also, let's say, also the ordering is the same, in the sense that the intersection is a fixed ordering, and we can also
Sorry, Rahman.
Yes.
In the first point there, did you mean U beta intersect gamma alpha, maybe?
No, gamma beta because it's Fodor lemma. So you have uncountably many conditions. So you have uncountably many ordinals below omega 1, right, in the U part. Uh,
Oh, I see. Okay.
oh, if you don't have it, then uncountably many of them are the same. But let's say it's more complicated. So you have these objects above, but then you can say that you know, you can assume that the U parts of all P alphas are growing.
Okay, I see.
Then
I
you
get
can.
Okay, yeah, thank you.
And also we can say that this common part, we call it U star. We star this part definition. We can say that even C alpha restricted to U star times V star is the same. Again, by uh, delta system lemma, Fodor's lemma, all of this. So this would be even more than enough if you want just to prove the specializing poset is CCC. Now, okay, now it's beautiful. Why? Because I have my conditions are like this. I have some level gamma alpha, and my U alpha sits here, V alpha sits here, plus this common part U star times V star, which is common for all of them. Then there is nothing here between gamma alpha and this part. I can put a barrier here, eta. So below eta, everything is the same. Below gamma alpha is the same. And then we have gamma beta, and these are these objects are sorry. Um, these objects are below V beta. Okay, like this. And then the same for U beta, V beta. Okay. Now, if you use Baumgartner-Malitz-Reinhardt lemma that says there are alpha and beta, so that V, this part, V alpha is maybe I write it V beta compatible with V beta. That means for any t in V alpha minus the core, and for any t prime in V beta minus the core, t is not compatible with t prime. This is Baumgartner-Malitz-Reinhardt. In the usual case of a specializing poset, you would say that, okay, I just take the union of two conditions and we are done. Now, if you pick such conditions, then you need to define these points are incomparable, and they have some mm, let's say if I have t in V beta, t prime in V alpha, and then they have a meet somewhere down. And now you want to define x and x prime, intersection between an x and x prime for x prime coming from U alpha and x coming from U beta. They don't have any relation because they are just objects with no ordering between them. So you want to choose something higher than this, but in a well-defined manner, because if you imagine that, let me show you a typical situation. So for example, if you have y here in U beta, and there is an ordering between x and y, so they have a meet somewhere in the U star. You cannot change it. And now you want to define meet between x and x prime and x, and also x prime and y. Both of them must be below x prime, and both of them you need to choose them high enough to overcome the difficulty I mentioned. Then you have to move the meet between uh, x and y. That is impossible because we are not allowed to move the meet in this condition, because finally the condition must be an extension of this, and we say that in the extension the meets are preserved. So so there is a difficulty here, because typically you want to be this point to be arbitrarily high, and then you are in trouble. So okay. So is it clear, or any question or explanation if you need? I would be happy. What they use is very, I think it's a nice trick, is isomorphism between conditions. So what does it mean? Okay, if you look at a condition, let's say this P alpha, U alpha, U alpha, C alpha, these guys, let me use U alpha, and this is a graph, and this V alpha with the T ordering is also a graph, and this C alpha is a coloring. So you can talk about isomorphism of weighted vertex graphs. What is that? Vertex weighted graphs. Whatever. So now what happens if you have uncountably many graphs with coloring, with graph coloring of finite graphs? Then uncountably many of them are isomorphic. There is one isomorph. How many? Countably many isomorphism types. But this isomorphism, moreover, it could be very nice in the sense that if you just prove using delta system lemma, you can say not only, for example, you can shrink this collection P alphas to a collection which are all isomorphic, but you can actually do many things. Like you say that, for example, the isomorphism is identity on this core part, and if you go from alpha to beta, from beta to gamma, is the same as you pick an isomorphism, which the set of isomorphism is commutative, not commutative. Yes, commutative. So why it is the case? You define on some object, you code all the information into a finite piece of omega, let's say, whatever. You code all the information, and this is isomorphic to all. So from P alpha you come to this code, and then you go to P beta. Then all of them are isomorphic, and the isomorphism are nice, and they preserve the core. So should I define this? Maybe I just say that we can code all the graph theoretic properties of P alphas into a fixed finite set, because we can also talk about the size of U alpha, size of V alphas, and then we shrink the collection to for each of them to a fixed subset of fixed finite. Sorry, this is not the right way to into a finite subset of omega, and then using delta system lemma, there are isomorphism system lemma. We shrink P alpha in X into P alpha in Y, y unbounded, y unbounded, so that for any alpha less than beta in y, there is an isomorphism phi alpha beta from u alpha into u beta, order preserving, and psi alpha beta from v alpha into v beta, and with many properties like phi alpha beta on u alpha intersection u beta is identity, etc. But there is one very important point here that these are which is C beta phi alpha beta x psi alpha beta t is the same as C alpha xt. So you don't move the color. And many other properties if you want. So for example, phi alpha beta, if you go to alpha to beta and then you go to beta from beta to gamma, then you get phi alpha, etc. Okay. Now we go to the same problem. Why the same problem doesn't happen? Because if you have a point in u alpha and you have some x prime, okay, here x in u beta, then you only need to define the meet if x is phi alpha beta x prime. There is one point, and the reason is that this isomorphism keeps this intersection, these intersections are there, and it's a common part. So if x is not, if y is not x, let's say this x, then y has a, you can by isomorphism come here, it's y prime. Now it is clear that if first of all there is a meet between these two guys, and also this meet is the isomorphism identity. So this happens that this also goes below y, and this goes below x. So you cannot move this. So what happens? You want to define. If you look at this, you don't need to define the meet between x prime and y, because the meet can be defined, and it's, I think, the only possible way to be. This is the new meet you want to define, and you take the meet between x prime and y prime. Still, it has some details to show that things work. So if you are at this level and you do this isomorphic shrinking, and then use Baumgartner-Malles-Reinhardt to make sure that T alpha, that in T parts the nodes are incomparable, they don't cause a problem in that sense, then you can define this way. But x prime and x, because x comes to x prime, you cannot, I mean, there is no candidate. Actually, you have freedom. So you can choose wx prime, wx prime to be above sup of t, sup of anything you want plus t delta t prime for t incomparable in t, and t and t prime comes from vp alpha union vp beta, whatever they. So yes. Then there is nothing in between to cause the problem, except there are some guys here for alpha, but then you can't assume that you have predecessors here and then handle the predecessors. So you handle the predecessors is enough. The same for here. So this is why I didn't talk about those guys. The guys below alpha or below beta falls down to the common part, and we don't need anything to say. Now you can choose Wx prime successor ordinal. That then you don't have to define mm, you don't have to define c, the function c over this. Actually, it turns out that this kind of picking works. And this isomorphism plays a crucial role here. Because of this coloring, you want to show that, for example, why it happens that you have I don't know, if you define a condition, so it define a condition R, and this R is extension of P alpha and P beta. This is natural. I mean, I don't want to define UR is UP alpha union UP beta, etc. The hard part was this intersection. And you want to say that, okay, what happens to if I have CR, let's say A T CR equals to CPT, why that thing about in the specializing triple happens is that if you come here, then you said, okay, the common part I don't want to talk. The problem is if these nodes come from P alpha and this comes from P beta, but then this P beta guy, if you by let's say this is C alpha AT, this is C beta BT, then by isomorphism, if you go from alpha to beta, it doesn't matter which way, but if you take phi alpha beta A, and if it is not B, then it has to be incomparable and the meat is higher, etc. And we are done. The problem is if this is actually beta itself. But okay, then we defined already the meat. Okay, so we have no problem. There are many. I want to say that there are many problematic situations, but most of them can be handled by isomorphism, going from one to another. But there is a particular property. Unfortunately, there must be a unique way, a unique particular situation that we need to handle, and is this isomorphism. Okay, so what happens to wide orange trees? Maybe I talk about this complicated situation. Imagine okay, just suppose that we work with the original definition still. We know that it cannot happen, but this is not my point. If we go to white trees, okay. Now, and I have conditions P alpha in PT with T white. I do all this disjointification, everything, but there is a problem. And that is, I cannot say V P alpha intersection T less than gamma alpha is the same as V P beta intersection T less than gamma beta. And the reason is that this is the core part U star, and then there is a core common part V star. But P alpha can have objects here, part of V alpha, part of V beta, part of V gamma, and this, like, because I can have uncountable levels, so they can peak. They are disjoint, but they are not high. So the difficulty is that why it is different from the other one. If you pick some node here, T, and some node here T prime, and you have x here and x prime. You cannot define the meet between x and x prime. It is defined already because it's in all conditions, right? So we can't change. So this causes a problem. And we know that we cannot have white trees with that definition. I don't know. Yeah, I defined what is the left specializing trees. Okay, that is at least something that we can try, because it doesn't imply that trees are orange or narrow. The point about that thing is, first of all, we have all the properties we want. But for example, what we can say, mm, we can, okay, it's a little technical, but how we overcome this situation that we have is that second version of Baumgartner, no, that Baumgartner model, Reinhardt, that we have infinitely many different things, right? So in this situation, I have the same thing. Okay, I pick those infinitely many good points, good conditions that are potentially compatible, but there is a problem here. Now, if we say what happens, why? Okay, now with this definition, okay, I was not very careful, but I hope you are convinced that if we pick in the previous case 2 points after many trimming to alpha and beta, then if we apply Baumgartner, Malus, Reinhardt, we can make sure they are compatible. And here we have all the good properties that if we make that object, then it is almost a condition, but maybe that delta part is missing. So this is why if I write p alpha plus p beta as that object which is defined like before, but it fails to be condition. The only way that it fails to be a condition is actually not only here is problematic, because here also you can have something from p beta here, but from something from v alpha here. Anyway, you have this kind of problem. Then you say that, okay, for any alpha and beta, I have a problem. I have a counterexample. That means I have a x, s, y, t, a quadruple, which maybe this x, s is in one of them, say p alpha, and yt is in p beta, or vice versa. They are good in many sense, but they fail to have this delta property. This is the only thing that fails. We can make sure about the other things. It needs some lemmas. So now I have this counterexample. Is a quadruple that fails to have that delta property. But these conditions are isomorphic. So if I fix some alpha, in this, let's say alpha 0 that we have, fix this alpha 0. If I go to this alpha 0, give me the counterexample, or if xs is in p alpha, I use isomorphism from alpha to alpha 0. If it is in beta, then I go from beta to alpha 0, and I do the same for yt. And so this way, I define a function from omega pairs of finite ordinals into this US star times, I don't know, V alpha 0, so times U star times V alpha 0, because I move everything there. So I get a quadruple here. And now by Ramsey theorem, there exists K0, not K0, K1, K2, K3, K4, such that if such that um, mm, yes, such that K0, K1, K4 is homogeneous for F. So that means, let me put it this way: if that means that I have X is in, let's say, P alpha K1 and another pair in P alpha K2, they have a problem. But they come from an isomorphism. I mean, because of this isomorphism, because of this I went into V alpha into P alpha 0. But then I have the same pair. That means coming from the same thing in P alpha 0 that makes the trouble. And this means that I have the points on the second coordinate which are not incomparable. The first points are not comparable when you use the isomorphism, but the delta falls below the delta of the. And then there is a stupid lemma. Is this I call it 4-node lemma. If you have a Hausdorff tree and theta is an ordinal arbitrary and you have 8 points different, but I wrote it like this because they are corresponding, and is that the delta of TISI is below theta, then actually you can find J and K, two different indexes, such that delta of TJSK and TKSJ are below the theta. That means what? That means if I look at the delta of that, here I use US star, right? I have a fixed counterexample in this which works for everybody. But this counterexample cannot, on the first coordinate, cannot move because isomorphisms are identity. So that means I have this delta x star. Sorry, I think I should put U alpha 0 here. Sorry. I have fixed x star, but then when I move yi is what? Is f takes x star, s star, y star, t star as the constant, the only color, and yi is homomorphism. You send it by alpha 0 alpha ki of y star. X star does not move, but this can move, and you also put S star to be Si to be phi alpha 0 alpha ki of S star. These are the witnesses. When you move them up, they make the counterexample, and also Ti phi alpha 0 alpha ki T star. And this happens that this actually is equal to for any I, and call it theta. And by isomorphism, you can show that actually delta Si Ti is less than theta, because they need to be, because P alpha 0 is a condition. And then we use this lemma that says that there are two indexes if you try to write it in a tree, you say that I have a node, this one with this one falls down, and also the other one with both of them falls down below theta. Sorry, if they stay above, you say that they stay above. Then you have 4 points. You will see that there must be two of them that with delta below theta. That means now by 4-node lemma, there exists J different from K, 2 points in 1, 2, 3, 4, such that what? Such that delta of Si T Sj Tk and delta of S Sk Tj is below theta. But just by isomorphism, if you look at them, these are phi of something, which is supposed to be a counterexample. This says that, in fact, if you use alpha 0, alpha j isomorphism and alpha 0, alpha k isomorphism, neither Sj, neither x star yj Sj, no, x star Sj yk tk and the other combination, there are two possibilities. None of them is a counterexample. So there must be two indexes so that you have the good property you want, and so you, p alpha kj is compatible with alpha kk or kk. This it's a little messy here, sorry, but is like really to see that what fails in this p alpha plus p beta, this object, then you realize that actually not too many of them can be incompatible. And then this is for this that gives a direct proof that under MA lambda, for every lambda arrangement tree, lambda white arrangement tree, there is an arrangement tree which doesn't embed into that. And then I use also this, but with a different argument using elementary submodels to show that it is consistent that there is a non-special tree, and but there is no universal tree. This is essential technique of Shella in his books for getting Suslin hypothesis plus there is a non-special arrangement tree. Still every arrangement tree is a special and an unbounded set, and that is enough for us. If we go to the proof that S does not embed into T, we didn't need anything except that we choose an unbounded set here. So if we have an unbounded set like this, that we have a C function is defined on them, then we can use just this simple counting argument, two of them with these properties. So this is enough. We don't need to actually make them special on all levels. But in contrast to what I gave in my abstract, I thought that this is okay with combined with Shella's technique to get there is a non-special tree, and for any white arrangement tree there is an arrangement tree and a function that makes a left specializing triple. But it seems to me difficult to combine white trees with Shella's technique. Maybe it is kind of impossible, I don't know. So I think I need to stop and apologize for being not very clear, and thank thank you for your attention.
Well, thank you very much for this talk. Thanks a lot. I think, yeah, maybe it was, I found it hard to follow at points, but it was super interesting and I want to understand it better. So I think you succeeded in making it very interesting.
Okay. Yeah, yes, I am writing a paper for a special volume on this.
A
It's not a
special volume, very good.
no, not in that sense. Yeah, a volume in honor of Judy Reutemann.
I see.
As I said in the abstract there, this is kind of technical notes. It's not really about theorems. It's about this technique, which seemed interesting to me. But I expected to do more, but for example, I don't know if it is possible to combine it with CH. So a model of CH, we don't know if it is consistent with CH that there is no universal Lorentzian tree. In the sense of weak compatibility, Veneria, Magidor, Vananen have claimed in their preprint that they have something in preparation that there they prove that in L you cannot have it for a strong embedding, one-to-one embedding, but not weak embedding. Something like that. So there are some problems, and these white trees, in particular, Omega 1 white trees have nice applications in topology and model theory. In particular, Iron for what was price games for uncountable structures. So it has connections with classification, and this weak embedding is related to those studies.
Okay, makes sense. Okay, great. Well, thanks a lot. I just want to ask quickly if there are any further questions or comments. Okay. Okay. Well, thank you again. It was very interesting. Glad you could make it.